Across the harsh deserts of the Middle East, where there is almost nothing but rock, hot wind, and burning sun, the country of Israel has done something that sounds almost impossible. They do not have a major river like the Nile or the Mekong, yet they managed to create a man-made river stretching hundreds of kilometers, carrying water from the wetter north and even from the salty Mediterranean Sea deep into the heart of the Negev desert. On top of that, they turned much of that seawater into drinking water inside huge desalination plants, so that today, a large share of the tap water in Israel is actually treated seawater. The question is simple but shocking. How can a small, dry country with more than half its land classified as desert or semi-arid build its own national river from scratch? For many decades, the Negev desert in southern Israel was almost written off as dead land. In summer, temperatures often rise above 40 degrees Celsius. Rain falls only for a few short weeks each year, and underground aquifers slowly drop lower and lower over time. In terms of natural water, Israel is unbalanced. The north and the coastal strip along the Mediterranean receive more rain, have lakes and some small rivers. The south is mostly rock and sand, with dry riverbeds that only carry water during rare flash floods. If Israel relied only on nature, most people would have to live in a thin strip along the northern valleys and the coast, and the desert would stay as a hard border for human life. After the modern state of Israel was founded, waves of immigrants arrived from many parts of the world. The population grew fast. Demand for housing, clean water, and farmland grew with it. Very quickly, the country faced a basic problem. How do you supply enough water for the whole nation? And how do you bring people, farms, and cities down into the south, into the desert? The first big answer appeared in the 1950s in the form of a technical drawing, the National Water Carrier. In simple terms, this is a giant water transfer system that combines open canals, tunnels, pipelines, and pumping stations. It connects the Sea of Galilee in the far north to the central regions and the edge of the Negev in the south. The idea sounded both simple and crazy at the time. Take water from the Sea of Galilee, pump it more than 200 meters uphill, then let it flow downhill by gravity through canals, tunnels, and massive pipes to the dry central and southern regions. But before a single cubic meter of water could be moved, engineers had to survey almost the entire route in detail. They measured the shape of the land, the slopes, the valleys and hills, the type of rocks and soils, which areas were too soft or unstable, where towns and villages were located, and where political borders might cause problems. On the hilly sections in the north, they used precise instruments to measure altitude, meter by meter. From that, they decided which stretches could be built as an open canal, which stretches needed tunnels blasted through rock, and which stretches required buried pipelines to avoid landslides or taking farmland. Where canals and reservoirs would be placed, soft soil was removed and replaced with compacted layers to make a firm base. Along the route, new quarries, concrete batching plants, and pipe factories were built, turning the 130-kilometer line into one long construction corridor. This first man-made river was about 130 kilometers long. That is the length of the national water carrier from the Sea of Galilee to the main distribution junction near central Israel. On this relatively short distance, the system has to overcome more than 200 meters of height difference, cross valleys, hills, and areas with soft clay. At the head of the system, an intake pipe sits under the surface of the Sea of Galilee and pulls water into a reservoir on the shore. From there, a chain of pumping stations pushes the water uphill, step by step, until it reaches a height where gravity can take over. The water then flows into the Beit Netofa Canal, an open canal almost 20 meters wide and more than 2 meters deep, lined with concrete so the water does not leak into the clay soil below. Farther south, open canal gradually gives way to large-diameter steel pipelines buried underground. These pipes carry water to distribution stations, where the flow is split into different directions for cities, towns, and farms. At full capacity, the system can move up to 72,000 cubic meters of water per hour, about 1.7 million cubic meters per day. Construction took more than 11 years, with thousands of workers building from the early 1950s until the system was completed around 1964. But the national water carrier is only the backbone. Over the following decades, Israel attached thousands of branches to this main line: urban water supply pipelines, irrigation lines for agriculture, reservoirs, pumping stations, and treatment plants. Today, the national water company Mekarot operates roughly 13,000 kilometers of pipelines, around 3,000 production and supply facilities, plus hundreds of wells, reservoirs, and treatment plants across the country. On a technical map, Israel now looks like a network of artificial rivers, with the national water carrier at the center and thousands of smaller lines reaching every city, town, and farming region. However, even this network could not solve everything. Rainfall became less reliable. Several dry years in a row pushed the Sea of Galilee down close to emergency levels. If Israel kept relying only on lakes, rain, and groundwater, the national water system itself could be at risk. In the early 2000s, after a series of serious droughts, Israel had to look for a new water source, one that was almost unlimited in volume. The only candidate was the Mediterranean Sea. The government and Mekarot launched a program worth billions of dollars to build a chain of large seawater desalination plants along the coast: Ashkelon, Hadera, Palmashim, Sorek, Ashdod, and other newer facilities. The goal was not just to fill small gaps, but to turn desalinated water into a main pillar of the country's water supply. Before seawater can become part of the national river, it has to pass through several layers of treatment inside the plant. The first stage is called pre-treatment or coarse filtration. Here, seawater flows through screens and metal bars that catch big objects: trash, seaweed, plastic bags, bottles. Then it enters sedimentation basins, where sand and heavier particles settle to the bottom. In some locations, the water also goes through oil separation basins to remove any floating oil. After that, the water moves to fine filtration. It passes through sand filters and activated carbon filters. Sand filters remove smaller particles. Activated carbon helps remove smells, colors, and some organic chemicals. Next, the water runs through hollow fiber membrane modules. You can imagine many thin plastic straws. The walls of these straws have countless tiny pores. Water passes through, but algae, larger bacteria, and very small particles are trapped. At this point, the water looks quite clear, but it is still salty. The dissolved salt is so small that it can easily pass through normal filters. The heart of the desalination plant is the process called reverse osmosis, often shortened to RO. Here, engineers use strong, high-pressure pumps to push seawater against special RO membranes. These membranes are like extremely fine filters. The pores are so small that we cannot see them with the naked eye. They are small enough that almost only water molecules can pass. Salt ions and many other dissolved substances are too big or too charged to get through. When the seawater passes through the RO units, it is split into two distinct streams. The first stream is called product water, or RO permeate. This is the water that has gone through the membranes. It contains very little salt and is almost like distilled water. The second stream is called brine, or concentrate. This is the water that did not pass through the membranes. Almost all the salt that was blocked by the membranes is left behind here, so this stream is saltier than the original seawater. The brine cannot simply be dumped into the sea at one point. If that happened, the local area around the outlet could become too salty and harm marine life. So the brine is usually mixed and diluted with more seawater and released through carefully designed outfalls that meet environmental standards. At first glance, the formula looks simple: seawater, membranes, fresh water. But there is a surprising problem. Sometimes being too clean is also a problem. Water that comes straight out of the RO membranes contains almost only H2O. It has very little calcium, magnesium, or other natural minerals. From a technical point of view, this very soft, low mineral water can slowly corrode some materials in pipes and storage tanks. From a taste point of view, it can feel flat and unnatural when you drink it. Because of that, there is another step called remineralization. In this step, the water is passed over or through crushed limestone or other mineral materials, or small doses of calcium and magnesium are added with dosing pumps. This brings the pH back into a safe and comfortable range, makes the water taste more like natural spring water, and helps protect the infrastructure. Finally, the water goes through a disinfection step using chlorine, ozone, or UV light to kill any remaining microorganisms. Sensors and control systems continuously monitor salinity, pH, pressure, flow, and many water quality indicators. Laboratories regularly test samples to make sure everything meets drinking water standards. Only when all these criteria are met is the water pumped from the Desalination Plants storage tanks into the national pipeline network. Depending on the year and the source, around half to 3/4 of Israel's domestic tap water today comes from seawater that has been desalinated. In other words, the man-made river that feeds Israel no longer depends only on lakes and rainfall. It is directly supplied by the Mediterranean Sea. When you connect the national water carrier from the 1960s, the 13,000-kilometer pipeline grid, and the chain of coastal desalination plants, you get a completely integrated system. Water can be moved not just from north to south, but in some cases even reversed, so that desalinated seawater can be pumped back towards the Sea of Galilee to help stabilize its level. With this engineered river, the picture in the Negev begins to change. In the Negev, water from the national system is split into secondary canals, pressurized pipes, and finally into drip irrigation lines that deliver water right to the base of each plant. Drip irrigation means that instead of spraying water over a whole field, each plant has one or more small emitters that release water slowly, drop by drop, at its roots. This reduces evaporation and waste and makes every liter of water do more work. Places that once had only rock and dust now show vineyards, citrus groves, vegetable greenhouses, and even date palm plantations and dairy farms operating in the middle of the desert. It is not only fields that change. Even some of the rivers and lakes in the desert are products of this engineered system. In the city of Be'er Sheva, the unofficial capital of the Negev, there used to be a dry riverbed and a garbage dump near town. This area has been transformed into the Be'er Sheva River Park, a long park with walking and cycling paths, bridges, an amphitheater, playgrounds, and a large, artificial lake of around 20 to 23 acres. The water there does not come from natural rainfall alone. It is mainly treated wastewater from the city, cleaned to a high standard, and then used to fill the lake and maintain flow. In many parts of the world, cities grow next to natural rivers. Here, Israel chose to build a city in the desert and then had to build the river to match that decision. Of course, the story of water in the Middle East is not only about engineering. It is also about shared rivers that cross borders, about agreements and conflicts with neighboring countries, and about debates over energy use, greenhouse gas emissions, and the long-term impact of releasing concentrated brine back into the sea. But if we look only through the eyes of an engineer, what Israel has built, a 130-kilometer national water carrier, a 13,000-kilometer pipeline grid, desalination plants that supply most of its domestic water, and parks and lakes in the middle of the desert, is one of the clearest examples of how humans can build their own river when nature does not provide one. In the 21st century, more and more countries are facing droughts, shrinking rivers, and falling groundwater levels. The key question is slowly changing from, which river do you live next to do you have enough technology, money, and determination to build a river of your own if you have to?